Today, we will be presenting the atomistic and crystalline structures of gold, tin, and copper oxide alloys, broken down into their component elements. So first, we will discuss the crystal structures. Gold is a pretty simple face-centered cubic crystal structure as seen in the diagrams here. But tin is a bit more complicated. Tin comes in two common forms. They are known as gray and white tin, or alpha and beta tin, and they have two different crystalline structures. Gray tin changes to white tin at about somewhere between 13.2 and 100 degrees Celsius, and gray tin has less useful properties as it's a powdery substance and has a face-centered diamond cubic structure. The more common and useful white tin, however, has a bodied-centered tetragonal structure. Copper, much like gold, is a simple face-centered cubic structure. Oxygen, however, normally in the atmosphere is a gas in its O2 form, but when cooled down to negative 219 degrees Celsius, it forms a face-centered cubic structure. This can vary, however, as oxygen, depending on the temperature, pressure, and the molecule, such as O3 or ozone, used in this cooling process, can form multiple other structures known as different allotropes, which all have their own lattices. But we will be using primarily the typical FCC structure here. Now, how do you get the coordination number of a lattice? For gold, as our first example, we will see here that to get the coordination number, you simply count the atom in the expanded 3D multi-unit cell lattice here. You take one atom and count its nearest neighbors to get gold's coordination number of 12. Now we go ahead and do this with both white and gray tin, as they have different coordination numbers due to having different lattices. And see here at the top, you get the coordination number for white tin of 8, and in the bottom here, the coordination for gray tin of 4. Now, how do you obtain the atomic packing factor? We'll use gold as our first example, and you see the equation here of, to get the atomic packing factor, you take the volume of the atoms used and divide that by the volume of the unit cell. Doing this for gold, you get 0.74. You see here again the equations used, as well as some of the intermediate steps, and use that to get the atomic packing factor for white tin of about 68%, and for gray tin of 34%. Now, how to get the theoretical density? Using gold as our first example, we will put it through the density equation, where you take the molar mass for the element, multiply that by the number of atoms per unit cell, and divide that total by the volume of the unit cell times Avogadro's constant. Doing this for gold, you get a density of 13.3 grams per centimeter cubed. Doing the same for white and gray tin, you get respective densities of 7.31 grams per centimeter cubed and 5.77 grams per centimeter cubed. Here's once again another demonstration of the equations used, as well as what the values mean. Now, let's get into the crystalline direction family and crystalline plane family, as well as the linear and planar densities of atoms. First up is gold, where we will put it through the linear density equation, in which you take the number of atoms centered on the direction vector, demonstrated here, and divide that by the length of the direction vector here. Doing this for gold using its atomic radius of 0.407 nanometers, plugging into this equation that is derived using a bit of trigonometry on this triangle here, you get the linear density of 3.474 atoms per nanometer. Now, to get its planar density, you take the number of atoms centered on the plane and divide that by the area of the plane. Doing that, you get 13.941 atoms per nanometer squared for gold. We do this again for tin, both white and gray, to get the values seen here. And to the right here, we see a diagram of a family of directions, specifically the 1, 2, 0 family of directions. Now, doing the same things for copper with the equations seen here, you get the values shown below. Once again, we use the same equations, of course, changed in respect to the lattices each time, and get values for oxygen. And to the right, we see a family for the 111 planar family. Thank you for watching our presentation. Apologies for my partner not being able to speak. He was unavailable at the time of recording. Thank you.